So up here, you'll see a little cam here. On the other side, there's another cam. There's some string pots under here. Geographically separated, there are 3 sensors for every axis of input. So if the pilot wants to roll, the flight controller is getting information from 3 different sensors. Just in case his foot went up underneath there and kicked this, or you had a hard landing, your elbow came down and broke something. These are practical things that happen all the time in flight tests. You need to have these geographically separated 3 to 5 sensors, depending on who you ask, and you vote on those. And those voting algorithms have time considerations and magnitude considerations. And they forget about things that happened a long time ago if you're in a different phase of flight. It's not super simple how to vote on things. But what happens is you feed into the flight controller what the pilot wants to do, and the inertial measurement systems are feeding into the flight controller saying, this is the attitude I want the airplane at. And if you have a position-based control versus a rate-based control, in this plane it's position-based in roll and pitch, and rate-based in yaw, then you can easily mask your control margin with the IMU. So you could sit there with the position forward 30 in a traditional aircraft. If you're flying along and you're like, holy shit, I'm all out of elevator. You know when you're nearly out of elevator. There's nothing else in the equation, right? You don't have an IMU saying, oh, I'm going to trim you up a little bit to get to a position, right? In this aircraft, you could be pulling it back 20% of its throw. Let's say you're trying to raise the nose on the aircraft. The IMU is saying, hey, I'm not raising, so I'm going to now increase the torque on the front rotors, decrease it on the back, increase the torque on the front, decrease it on the back. And I'm sitting here happily at 25% of my throw, thinking I got more margin in the stick, but masked by the IMU, we're completely tapped out in torque. And you can very easily do that in yaw, give clockwise and counterclockwise rotors, spinning you around, and all of a sudden you want to perform a secondary maneuver. And that's why you have to prioritize those things. So you get into flight test here, and you need to know that. And that center thing right there shows you the margin that remains as a function of what you're putting in as a pilot and what the torques are coming out. When we were ready, we started getting the cockpit ready, put some super safe devices in there, looking at temperatures of everything. Temperatures are one of those things that will just kill you if you get it wrong. The motor, this is a little bit of diversion. So propellers. The propellers in this aircraft, we went to 35 different manufacturers. I'm like, what are we going to build, what are we going to buy? Obviously, we're going to buy propellers. Everybody makes propellers, right? We went to 35 different manufacturers of propellers, and they said, you're crazy. A fixed pitch, edgewise flight rotor, 11-foot diameter, we're not going to make that. Half of them were liability, the other one thought it was just stupid. So we said, we're going to build our own. So we started to do some really basic models. We went to the internals of the propellers, to reading about propellers. Anybody know about the fatigue life of propellers? And aluminum, carbon, or composite versus wood? What's interesting about that? That wood is the only material without an FAA-rated fatigue life. It'll run forever because of the drain boundaries and the damping coefficients of the material versus the way that you stress composites. Really interesting. So we said, okay, there's something there. And one of our bigger risks is the vibrations. So let's get something in there that dampens vibrations. Foam isn't very good, but wood's pretty darn good. So we started with a wood core. We stacked up the wood, and in the interlayers, we were looking at the centrifugal force calculations. We're saying the wood isn't quite strong enough to hold it out this way. So we used unidirectional fiberglass in between every layer of the wood. People wouldn't machine these things, so we brought it to a furniture maker. We said, put this on your big machine, build this out. Once we got that done, we peppered the things with strain gauges to validate our Excel spreadsheets, Microsoft Excel. Put wireless transmitters in the middle, strain gauges, those are all rosettes out there, so we didn't have to know what the direction of the strain was. We could just lay them down, spin the things. We brought these things to failure. This is just a static test, right? So you've got centrifugal force, you've got drag forces on the thing, and then you've got this bending force in the aircraft, or the propeller blade that's causing lift. And we're hanging these things on here. We got to 10 times factor of safety, was our target for the rotors, because we were unwilling to compromise on a rotor failure. This was the ultimate test, to hold somebody up, right? Got to UV coat the things, and we got into the dynamics of the thing. We wanted to look at the flutter of the rotors, right? These are going to be an edgewise flight. We spin them in this cage. We put strobe lights on when we're ready. We put them on here. Edge wear in the propeller was a big issue. We met every morning. We got in the plane. These are just some fun pictures. Team pre-flight. Get everybody together. Get in the plane. And this is a little bit fun. I think this was online. but I'll just talk through it while it goes. So there's some sweet music. Anyway, this is first flight right here. And those of you in the controls world, you can see the stingers on the wing and the tail. And we did a lot of calculations to determine our PIDs. We take the thing up in the air and it's a little bit stable. We start to get more and more stable, and see how stable and beautiful that is? Then we start getting maneuvering flight. Can't do that in a fixed wing airplane. Take off and just roll backwards and get out of dodge. It's really fun. Yaw rates, so these are some of those basic physics things. How much torque are you putting in? What's the moment arm? How fast can we turn in yaw? Side slips. This particular side slip actually ended in vortex ring state. At just over 100 feet coming in, came down against the rotors and flew into the wake and had to side slip out of it. This is, I don't know, 10 degrees forward. You can see the double slotted high droop in the flaps to change the chord angle. So as these things tilt forward, it gets to the point where you're downwashing on the wing. You want to get that chord angle as high as possible, mean chord angle. This is our, I think, our 100th flight. Taking the thing off, it was so fun to fly that we found an excuse to fly it every time we could. This video, unfortunately, is almost a year old, so it's a lot of vertical flight. We've been moving further and further forward and getting on the wing, so getting fast enough with these things coming down. We have full down to 0 now, and we shut the power off and see if we can glide. I don't know how much more is this, but that's the vertical flight. This is really interesting. This guy that flies helicopters, right? Slope landing. What's the trick in a slope landing? Or slope takeoff, even better. The trick. I mean, okay, so it's a trick question. No, it's not. You got to remember that the disc of the helicopter isn't fixed frame with the base of the helicopter. So if you're going to take off on a right slope here, as you start to pull up that collective, you're going to start to move your cyclic to the right. And you're naturally going to start to pick up that left skid. But what's happening to the disc has gone level, and then the disc comes straight up, right? You can't do that in a fixed frame aircraft, right? So how do you land in a slope or in a crosswind? Do you land into the wind? So the wind's whipping. This is a 32 knot day. The wind's coming straight at me. And you've got a cast-ring nose wheel, and you've got brakes on your brakes on your main gear. And you say, well, obviously we always land into the wind, right? We've got more controllability with the weather vaning tendency of the tail, and all of a sudden you can't put it down. Because every time you put down the cast-ring nose wheel and you start to drop the back, you start whipping backwards. And the worst thing to do is going backwards when you land. That's just not a good position to be in. So as we're doing this, and you guys are way smarter than me, you probably would have predicted this. I didn't. And I got up there and I was like, holy shit, I can't put this thing down. And I had to turn this thing about 45 degrees, lock the right brake, put the wheel down, and then as you let this down, you can't keep the rotor disc over as you gently let it down like you do in a helicopter. You have to rethink how you're landing. So autonomous aircraft, eVTOLs, they're kind of synonymous in many circles. And you start to think about writing a auto landing sequence, and you start to totally change your perception of how we're going to approach the helipads. This was a fun day. We did have a fire in the cowling during flight. It's pretty scary. You're up there, you start to smell strong electricals fire, and we were able to land it, pop in. This is just to remind us that real shit happens. That particular issue is because I didn't properly review a design where we had an electrical connection that in the stack up had some polymer in it, and it got hot, it reduced increased the contact resistance, something got hot, caught on fire, things shut down, put the thing back together. These were fun tests. We got up in a stabilized out-of-ground effect hover, and remember, we claimed to ourselves that we could lose any motor and we could still land safely. But it takes a fair amount of gonads to be up there and be like, you know what, I'm gonna now shut that down. And you start to fall, because you're gonna have an uncontrolled yaw, but you're gonna lower down, and you're gonna keep the rubber side down. And you see how close the prop is to the ground there? It's about 4 inches off the ground, but we were able to achieve that. This right here was another pretty nasty landing, where we had a test device on the dashboard measuring high fidelity CAN messages, and it fell off and it severed both IMUs at the same time. So both IMUs are gone. You've got no inertial measurement, so now you have an open loop control. And what do? kill the batteries. You got to come down, right? So we landed on the tail, took out the me and Ava, that's the we. Put it back together, got it flying. So let's say you want to fly from airport to airport to airport. You want to refuel this thing. How are you going to do it, right? So this is Ike Riley. He's a rocker. He's a great guy, but he sold us his 1982 Eagle bus, and we put a helipad on top of it. We opened it with solar. We put a 45 kVA generator down in the back and a 1,000-volt, 100-kilowatt AC to DC converter, because we need to have 1,000 volts DC nominally to recharge the aircraft. And everybody knows battery charging, you can't just dump a bunch of current into the things blindly. You have to have a queue communication between your battery monitoring system and the aircraft. So this is Martine, our partner and sponsor and a friend, just checking off the test flights. Tethered hover, landing and pickup, free hover testing, free hover out of ground effect, in ground effect, OEI testing, ground initiated transitions, hundreds and hundreds of flights, just getting through them. This, I don't know what vector angle we're at there, maybe 20 degrees forward. We've gotten up to about 75 knots forward, which gets us on the wing. And that's inspired us to design a new aircraft. And the new aircraft is using the same first principles engineering. An electric vertical takeoff and landing aircraft, energy storage, specific energy density. Diesel Jet A, 100 low lead, it's not getting any more energy dense. And everybody's giving high fives to each other at Boeing when they get 0.4% better efficiency, right? Because that's pretty damn good. But specific energy density of batteries moving 5 to 8% per year, right? So there's got to be a point where it comes to parity. Anybody know the efficiency of a jet engine, roughly 20, 25, 30, right? Reciprocating engine, maybe about that. Really, really good ones, maybe higher. But the conversion efficiency, battery to propulsion in electric, what do you guys think? Take a guess. What's that?
95.
Not quite that much, but close, very close. I mean, if you're in the 90s, you're doing a really, really good job. The propulsive efficiency of the propeller is obviously kind of tearing both of them down. But that specific energy density of batteries is going up. Jet A and low lead is here. We're 20 times different right now, but our conversion efficiency is maybe a 3 to 1 or 4 to 1 difference. So maybe 5 to 1 difference right now. But we're still going up 5 to 8% year-to-year compounding. Obviously, the power conversion propulsion design consumes that specific energy density. The more battery you can get in there because you have lower empty weight fraction, gives you a better aircraft. And of course, your L over D determines if you're operating, in a good portion of that curve. It gives you effectively, those 4 parameters give you the range of the aircraft. To make practical electric aircraft, we have to thread those things together very, very carefully, because a lot of times, aerodynamic efficiency doesn't support empty weight fraction, right? So we want a nice, long, big wing, and we're like, whoa, that's got, small thickness ratios. If you have a 100-foot wing and a glider, empty weight fraction kind of goes to crap. So let me just look here. Am I okay on time? You guys getting bored? No. This is how Beta was founded, and this is the path we're on right now. Now we're up to about 30 people, and we have found ourselves in a really, really unique position. All because of that one little comment about, I'm here because I just like aviation. And we're going to elicit critical thinking in aviation by building something. And while a lot of folks create a big stack of papers as a design study, which are awesome, super interesting to read, but it doesn't fly. And we found ourselves, a little company in Vermont, in an awesome position, competing with all the big guys in this next design and having a pretty sweet customer and contracts for building these aircraft. So I think that's all I have for a presentation. Apologies, it wasn't super academic, but just wanted to kind of tell a story that was my own little personal path after lucky enough to come down here to where we are as a business, and now it's grown from this this little kernel to a team that's just awesome. And we're having a lot of fun, and we're flying everything every day. I've tried to fly different aircraft every day of the week, which is just like I've never dreamed of something quite as fun. And hopefully, well not hopefully, by the end of this year, we'll be flying a 7,000-pound eVTOL that'll do 250 nautical miles, which I think is, we already flew the heaviest eVTOL ever, which isn't something to brag about in aerospace, I know, but just as like something. And now we're going to fly the longest range. So that's all I got. Any questions, thoughts, comments? Yeah.
But also about how you manage the project management aspect of it, because it sounds like you got to each iteration pretty quickly. And when you're answering that, can you tell us how long it took you to get to the Hangar or Fletcher?
Sure, I'll start with the easy part. Whole project was 10 months long. We went through probably 8 weeks of design turn at the beginning, figuring out what the heck we were going to build. And then by, and I'm just doing math in my head from 7 to 11, it took us 4 months to complete the Iron Bird. It took us 3 months to get that entire system kind of debugged. And then overlapped with that a little bit, it took 4 months to get the FAA to agree to allow us to fly it. And there's 3 aspects to a phase 1 flight testing authorization called a letter of authorization, or a program letter. One is the operational restrictions, like where and how you can fly something. 2 is the airworthiness, and 3 is the pilot licensing requirements. And the pilot licensing requirements were the big holdup. They said, okay, that's fine, I'll fly it over anybody's head, I don't care about the pilot or your test team, just do it over there. But then we went to them and said, who's allowed to fly this thing? Is it a helicopter pilot? Is it a fixed-wing pilot? Do they need a multi-engine rating? Do they need a high-performance rating? Do they need a complex endorsement? Like, what do they need to fly this? And they're like, well, obviously, they need a powered lift rating. Well, it turns out that the FAA, there's the notion of a powered lift in the military. There's no certified powered lift aircraft. Therefore, there's no practical test standards for a powered lift aircraft. They had issued 6 powered lift certificates to ex-Osprey pilots. They had since pulled them back, and for the 609 and a few other things, they were giving out specific letters of authorization to really experienced test pilots. And we said, well, that's a bummer, because we can't afford one of those guys. And we wrote a Part 141 style flight school curriculum, built the simulator, went back to the FAA, and after going to Washington, going to Portland, Maine, going to the ACO down here in Boston, back and forth, we ended up going to our local senator, Senator Leahy, and saying, you've got to do something about this. And this is like, you know, social engineering. We go to the senator, we go to Bernie, we say, you've got to help us out. And they started putting pressure on the FAA. We talked to the commissioner of the FAA, who finally allows us to get our flight school accepted. And I think we're the only eVTOL company that can now issue letters of authorization to pilots to fly eVTOLs. So we have pretty neat. So I'll answer your second question now. Project management, as you might imagine, that's probably, that didn't come up. It just, when you get into the rhythm with a bunch of people who've done a lot of technical things before, somebody says, I'm going to deliver you a propeller. There's no Gantt charts or formalized bills of materials and purchasing departments and whatever else necessary to get it done. The person doing it does all of that. And in very fast, efficient prototyping teams, even now, when we've got a 30-person team, we don't have an ERP system, we don't have a purchasing department. You as the engineer are responsible for delivering a battery on June 15th. You got to get that all figured out, and there's no loss in translation between the supplier and the purchasing department and whatever. And we have quarterly goals, and that's it. There's nothing higher fidelity than that. And I fully recognize that at some point that has to change as our business starts to get, you know, proctology exams from the FAA and other things. But right now we really don't have the type of project management, and I hope there's nobody in here doing or teaching the project management or engineering management course, but I've worked for Raytheon, I've worked for a couple big companies, and we spent more time in prototyping, and this is very different than production. Because you can waste a lot of time in production if you're missing a conductor pin on the upper left corner of the aircraft, or it's sitting on the end of the line. But that's not the case in prototyping. Things change too quickly. So there really is no formal project management aside from people keeping their promises.
Changes in how do you communicate between different people who are responsible for different things? Because if you're trying to iterate very quickly, isn't it easy for something to be overlooked because someone thinks it's someone else's responsibility?
Not in a really small team. So our company, even at 30 people, every morning, 9:15, we get around a big table and we hash out what everybody's doing that day. And we make sure people are responsible for particular elements. And another thing about the culture of our business, which will expose how this works, we have no vacation policy. Anybody can take any time off anytime they want, as long as they don't let their colleague down. So if they're working on a project with somebody else, they don't come to me and say, hey, can I take this time off? I don't care if they do. They go to their colleagues who are depending on them to create a connector that goes to the flight controller, that goes to the motor, and you say, work that out, and if you lose the respect of your colleague, you're out. And that's how we manage that. So people are operating with absolute accountability of keeping their promises. So again, that's something that works when everybody's touching and feeling everybody else. We've arranged even the desks in where we're working with people that are communicating with each other technically within the aircraft, such that they aren't more than 10 feet from the person who they're, if you're doing connectors and wiring, and that this guy's doing flight controllers, and this person's doing inverters, you're sitting between them. And there's no way around it. And we're shuffling that constantly. So I apologize for not having a good answer for you, but that's how we're rolling right now. Yeah?
You told us to test an app or a SIM to give the feedback.
Yes. So we've been quietly developing autopilots and synthetic vision and a whole bunch of things in an app called Xavion, X-A-V-I-O-N. And yesterday we released on the App Store the 3D instrument approaches. So everybody's probably familiar with instrument approaches, flying the needles, ILS is GPS with LPV. The 3D instrument approaches will actually put tunnels in the sky, showing you those step downs, showing you the glide slope so that your velocity vector is pointed at the airport no matter what altitude or direction you're flying, and that velocity vector is straight down a shot in synthetic vision. So we call these 3D instrument approaches. So no longer are you looking at this right here. You're looking at a tube that you're going to fly down. And I'm aware that there are hoops in the sky with other people, but this is a little bit unique in the way that it's set up. Yeah, if you guys want to, if you're out flying, test it out. Just take Xavion, throw it on your phone or your whatever, and get a Sirius or, not Sirius, excuse me, who's the guy that makes the ASB receivers, the really good Stratus, yeah. The Stratus, they seem to be really stable systems. Any other thoughts or questions? Yeah.
Can you talk about, I think I hate this question, but I might as well ask it. Can you talk about scaling or any sort of plans you have for that? Like, how do you scale up this very tightly in a team?
Yeah. So I have a goal to keep, the last business, or 2 businesses ago, we were at 325 people. And it got too unwieldy. It was too much growth, not enough camaraderie, things start to get the culture starts to break. And culture being absolutely paramount, as I described a second ago, within our business, how we operate. My goal is to keep it less than 40 people and have very, very high-performing engineers and giving them all the tools to be the most efficient engineer they can be. So instead of asking the question, who do we hire to do that? It's, can you figure out a way to make the time to do it yourself? Can we give you a tool to be more efficient? Can we offload you from something that can be outsourced? Making parts, it's great to get engineers building composite parts the first time. But once you do it once and you can speak the language, you understand the problems, you get it elsewhere. So step 1 is to not scale. Like, we're not pushing repeat on people. It's keep it tight and small. and then recognize what you're good at, right? What does success look like for us as a business? To me, it's not to grow to a $4 billion business making 200,000 or 2,000 aircraft a year. It looks like us getting to the point where we have that aircraft that now can be type certificated or is type certificated, and it gets handed off to people who enjoy clipboards and manufacturing and project plans. There's really good engineers. And by the way, within our team, there are 4 or 5 engineers that will transition over to that new team. So the scaling isn't trying to take a good engineer, a good development, research and development engineer and saying, now you're going to manage production of that thing you designed 4 years ago. And they're like, oh, I want to design something new. That's how I roll, right? And the better thing is to hand that off, in my opinion. Now, there's certain people that will go with that, right? And so then the scaling will be a sidestep from the core team over here to build a team that now is good at production. And maybe do that 4 times, right? So the core team and what we're talking about here doesn't necessarily get very big, so we don't need to scale. And could be totally wrong, and that may be totally infeasible, but that's the plan right now. Yeah.
What resources do you use when you were stuck on a problem, especially since you're in Burlington, in Vermont?
Like technical resources or like human resources outside the company?
Technical and business issues.
Yeah. So we used a variety of different people that I had. So if you're talking about like stuck on a technical problem, how do we get over this specific hurdle? One was to call up, and I won't use names, but you can imagine the top 5 aerospace companies. Find the best person on LinkedIn that you can find designing propellers. Call them up and say, hey, we have this little project, it's up in Vermont. Can you help me out? Here's my problem. And it turns out that smart people, when they realize you are engaged and passionate and care about what you're doing, they'll answer your questions. And they could be the lead development engineer at pick one of the 5 top aerospace companies, and they answer the phone, cold call, and you say, I need a little bit of help on this. And that happened several times. We got stuck on, for example, the composite layups on top of the propellers. Talked to this guy, 70 years old, the guru at a national propeller manufacturer, and he's given me more insight about propeller manufacturing and where they bumped their head in the past than any book ever could. And you're describing and using them as a sounding board on every one of those little challenges. So just pick up the phone and call people. If you're nice and polite and professional to them, they answer your questions. We didn't use, if you're asking, like, did we go to a local university and use their FEM models and whatever else, we didn't do any of that. Really, again, ask the team internally to find a way to make themselves efficient enough to solve the problems.